About three integrals when it's constructed.
All right, so thanks a lot. I'm very happy to be back in one of my favorite places of the world, especially that I'm so honored to meet again my former supervisor, colleagues, and other people. So and I will report today what I have been working on in the last years. So this is an attempt to compute the full set of integrals that are needed for Higgs plus jet production at 3-loop. So this collaboration started with Johannes Hen and our PhD student Chung-Won Lim. And recently, we are joining forces with the group of Thomas German and Lorenzo Tancredi, together with their PhD students and junior postdoc. All right, so just to set the stage, let me recall what it is known. So everything started a long time ago with the calculation of Johannes for this non-planar diagram, but then people moved forward, and especially was thanks to the work by Pierpaolo almost 10 years ago, in which they calculated this integral with the resources that were available at that time. And as you can see, we had to wait almost 10 years to go further in the evaluation of these 3-loop planar integrals that was recently computed. And then successfully at the beginning of this year, so we provided the first non-planar results, the complete set. All right, so with this in mind, we want to continue in their evaluation for two different aspects that I will describe in the following. But before I go there, I will try to tell you what's the plan of my talk. At the beginning, I provide a sort of motivation between the pheno side and the formal side. Then I will discuss the algorithms that we are currently using for computing these Feynman integrals. Then I discuss the approach that which somehow is a standard approach to calculate these Feynman integrals, and then in view of the effort for the calculation of steady amplitudes, I will discuss where we are and what we are looking right now, and finally some conclusions and outlook to our work. All right, so we are here somehow to go further in precision physics. Yesterday, we heard from Costas that n-cube LEO for 2-to-2 process is somehow understood. So what about we go further and try to go for n-cube LEO? And this is our main motivations in here. So with the new experiments and new developments that are currently provided, we need to go further in high precision, and this is exactly what we need for these kind of processes. But also, if we look from formal aspects of these scattering amplitudes, and we look, for instance, our supersymmetric theories like n=4, we see that these kind of integrals with one of-shell leg is usually called like form factor, and they have very interesting properties. And this is what we are also looking at. And in particular, we observe that this particular integral family display a sort of cluster algebra that I will explain later on in my talk. And these are surprising evidence of this interesting Feynman integrals. All right, so with this in mind, let me start with the algorithms we use for computing these integrals. So just to set the stage, I don't want to be very pedestrian in this because this is like common knowledge for everyone in here. So this is what we start considering when we draw a Feynman diagram, and then as soon as we translate this Feynman diagram into a Feynman integral, we obtain these guys, like, of course, represented by the propagators. And in order to express this integrand as a rational function, we need to add additional or auxiliary propagators, which we call ISPs. But then it was known long time ago that Feynman integrals are not independent. Instead, thanks to the dimensional regularization, we can understand, we can cast them in terms of differential equations. But then, assuming that we find a nice set of integrals, we can broaden them in a very nice basis, which is somehow called canonical basis. This is, of course, provided that the set of integrals admit a logarithmic singularity. And this is indeed a result of more than 10 years ago by Hen, in which once we have this epsilon factorized form, in which this guy in here, this matrix in here, just contain logarithmic entries. we can provide a complete, a full differential equation for this guy, and everything is already solved. We just need to iteratively integrate order by epsilon, and then we are simply done. This is our goal in all the calculations we are currently doing. And to achieve that and really to find the epsilon expansion of these Feynman integrals, we try to follow this workflow. So we run a first numerical reduction in which we understand the master integrals that will appear per sector. And then once we know the master integrals, we can rely on two different approaches to understand the proper set of integrals that will appear in there, where they are in canonical form. And as I mentioned before, so we use a code which is called D-log basis, and also the known UT integrals in different subsectors. So you might have seen that adding different dots might help the problem. I will explain why is that the case. And then as soon as we have this set of integrals, we can process further and find our differential equations. This has been implemented with the aid of light red and also parallel implementations. And then when everything is done, so we integrate order by order in epsilon. For this, since the alphabet is not that complicated, as I will show in a few slides, so we can easily integrate in terms of generalized polylogarithms. And finally, we validate our results. To do so, we use PySecDec, and recently we made use of Finetrop, really to evaluate our integrals in one physical region and also physical region with the latter one. All right. Let me go a bit into detail what we have done during this calculation, and let me recall what a D-log integral is. So imagine that I start with a given integral, and if this integral can be expressed in a product of D-log forms, like in this way, I can immediately say that this guy is in D-log form. Otherwise, if at certain point it manifests a double pole or something like that, I cannot claim that this guy is a D-log form. And interestingly, so we don't obtain like single integrals in all the cases. Instead, what we obtain are linear combination of these kind of integrals with linear propagators. And this has been automated in the code by Pascal Basser for a long time ago. And so if you are new in the calculation of Feynman integrals, you can write this code and automatically get a set of integrals. Unfortunately, this is not complete. So because in order to complete the full set, we need to enlarge the integral family we need to consider. However, the integrals that are missing after running this code are the easy ones. And for instance, we realize that this integral, we need to include it by hand. This is, of course, not a D-log integral. It will manifest a double pole, in particular because of the presence of this bubble in 4 dimensions. However, if we try to look closer at this diagram, we see that if this loop is in 2 dimensions, the other loop in 2 dimensions, and this guy in 4 dimensions, it can behave as a UT integral. And this is exactly what we did. What can be seen, like as soon as we pass from d equal 2 to d equal 4, it's simply like putting a dot in one of the internal lines. And the same for the other one. And then just to account for the leading singularity, like is in here of this guy, is simply a leading singularity of a box, which is S times t. And automatically, this guy is a very good candidate to be in a UT integral. Then somehow everything is under control in this case. And then we can proceed further. This is what we did for our calculation. So in the first part, we revisited the old results for planar topologies. And we also went further in the first evaluation of non-planar integrals. This is just a summary of what we obtained. So in particular, let me recall that this is the alphabet of this integral family. So let me from until here, everything corresponds to the one loop Feynman integrals. And then as soon as we go to two loop, this new letter appears, But then for this integral that I'm underlined here, these two new letters make their appearance. So it's not as simple as before. However, if you see the expression of the alphabet, you see that always this the kinematic invariant t is always linear. Then there is not really an obstruction to perform the integration. All right. So then with this in mind, so we express everything in a canonical form, and we proceed to the actual integration. So since the kinematic scale, this p4 square or the of shell mass can be simply pulled out and recover as a phase. We define this dimensional radius, which we call Z1 and Z2, just to give it a name, and then we iterate order by order in epsilon, and this we do it up to transcendental weight 6. In practice, so you know that in principle one can take any path that is not really is not a problem because it is homotopy invariant, this relation. But for the sake of simplicity, to also look and we got inspired from very old result by German Remedi. So we took two different paths. So like one along Z1 and the other path along Z2, like one in such a way that, let's say, if we integrate over Z1, the other one becomes constant, and then we integrate over the other one. So this is what we did. Of course, we need to be a bit careful when we do the analytic continuation, but that's not really an obstacle. All right. So then as soon as this is done, so we have everything in terms of arbitrary constants, and we need to fix the boundary conditions. So for the planar case, everything is somehow trivial because you simply fix regularity conditions and then you are done. But for the non-planar case, apart from the regularity conditions, we also need to look at additional constraints. And these additional constraints are given by the study of physical and non-physical thresholds. So roughly speaking, what we do in there is like if we have the integral in a physical threshold, we said, okay, we would like to have this integral close to this physical threshold. Therefore, I will have a behavior exactly in this way, which is alpha I corresponds to a letter. But then it means that since at the beginning, I'm assuming that my integrals are ultraviolet finite, it cannot develop further singularities. Therefore, it gives me additional constraint. And this additional constraint allow me to restrict the number of boundary constants that I need to consider. Once this is taken into account, I realize that everything can be expressed in a single boundary term, which is the easiest one that can be obtained at all orders in epsilon. Okay. And then finally, so there is the numerical evaluation. So this somehow, in order to perform this integration, we rely mostly on polylog tools and GNAC to evaluate them numerically and also to reconstruct with PSLQ and the boundary constants in terms of zeta values. And just to show you the integration domain that we have in here, so the gray region corresponds to the Euclidean region. And interestingly, for all planar and one of the non-planar integrals, all of them are real value quantities. But then for the integral that contains new letters, so we obtain these curves in here, and there will be exactly a region which is, I think, is this fourth region that all expressions are real value, and this is what will happen exactly in there. And then just to compare our results, especially for the new integrals that we calculated. So we made use of PySecDec, and we chose this unphysical point, in which everything is real. But also, so we look for integrals that are already finite, and compare our results with Feintraub, finding fully agreement. Okay. This so far has been the evaluation, but let's look in detail of what we obtained. So we found, as I mentioned at the beginning, we found two new letters. And these two new letters are somehow related by the symmetry. So just the exchange of P1 with P2. And if we look at the symbol level, they will start appearing at weight 4. This is somehow shocking because from the infrared factorization, we don't expect new letters to appear at this weight. So we somehow expect that there will be a cancellation at weight 4 once we compute the scattering amplitude, or we use a different basis of integrals. Okay, in the same way, so it was understood a long time ago, clustered algebra, but recently these people look into details at this particular integral family and consider this sort of clustered algebra. And roughly speaking, is that you start with two nodes, and then you start mutating the different nodes one after the others. And after you do all different mutations, you go back to the original one. And then you can see in here that that the letters A1 and A3, for example, and A1 and A5 never appear one next to the other. So this is somehow called adjacency condition. And this is what was observed from explicit examples. So these people consider what happened for the two-loop integrals of Germar and Remedi, and also the expression that Pierpaolo and collaborators computed in the past, and they realized that this adjacency condition was satisfied, namely that these two letters, these three cannot appear one next to the other. This, of course, simplified quite a lot the calculation. But for the tennis score, it was not completely checked, maybe because of the way how they integrate. But we did it, and then we observed that everything is satisfied, like for these integral families. But for the one of the tennis score, it was not satisfied anymore. Then, but again, this is at the level of integrals. And if you look at these integrals, so this just is a symmetry between P1 and P3. However, so recently we calculated the contribution to the form factor in n equal 4 Superior Mills, and we observed that this discrepancy is healed once one considers the whole integrand. This has been already done, and so we don't expect that things have to hold for individual Feynman integrals, but for integrands, but for scattering amplitudes. Okay, so yeah, and there are also preliminary observations for the calculation of Feynman integrals. So as I mentioned, we continue looking at their evaluation, and we obtain that this integral in here generates yet another new letter that is completely related to this one. So roughly speaking, this is like this letter that appears in here is the leading singularity of this guy. But that's not the end of the story, unfortunately. And we have a square root. But okay, this square root appears in many different ways, but it's only one. So at least we have a square root, but it's only one. So we can deal with that. And this is currently the status of our calculation. Now we are joining forces to calculate the scattering amplitudes for Higgs plus jet production. And then, so everything is somehow known, like planar integrals, and recently also subsectors were known and they were made public. And then, to start, we always start with the simplest case. In this case, the simplest case is the leading color, but different to gluon amplitudes or something like that, we also need to calculate, or better, to consider non-planar diagrams. And these are the non-planar diagrams. I'm just restricting to topologies with 10 propagators. We need to consider these guys. So one of them is already calculated, and the other ones, they are in the making. But so, okay, we have these one that are true parent topologies, but this one, because of the triangle insertion, it will be reduced to lower topologies that have been observed. Then where we are, so as I said, this is in collaboration with these people, but most nicely we can look at it in this way. And where we are, well, we have already the canonical differential equation. So for this guy, and this guy contains a square root that I showed before, and just pictorially what we have. So everything is calculated on the maximal cut, because maximal cut is trivial, and then also subsectors, because we extensively made use of D-log basis and also the knowledge of UT integrals, but there are a missing part. Like this missing part corresponds to making the integral that appear in the top sector completely D-log, and also a few subsectors that we are missing. And this is somehow an obstacle of the code. So we try to avoid doing things by hand. Then probably looking directly at the subsectors will shed light, and this is currently where we are at. And then if we want to complete the full set of integrals, so the green integrals is that we have already completed the epsilon expansion. Unfortunately, we were unlucky enough that these integrals didn't appear in the leading color approximation, but they will appear in the full expression. And out of these integrals, I would like to recall this one, which we have observed to be the most difficult one. And it's because, well, it has it has 371 master integrals. And in the top sector, it has 19 master integrals. So the canonical differential equation on the maximal cut has already been obtained. So to do so, we use the knowledge of n equal 4 super-Jamils. We know that it will be universal, that the result will be of universal transcendental degree. And once we have this candidate of integral as an input, we can run initial, and then we obtain all candidates. But of course, we are missing the complete differential equation. However, so all subsectors that appear in here are obtained in the other subtopology. So we expect that it will take time, but the efforts we are doing for other topologies will be recycled in this calculation. All right. So with this, I would say I should stop. So let me just summarize what we have reached. So we have computed the first set of non-planar families, and to get experience on the evaluation of Feynman integrals, we revisited planar families. We found 2 new letters, and apart from the 2 new letters that we have already published, there are additional letters. One of them includes a square root, and then we want to go further and provide the calculation of the scattering amplitudes for Higgs plus 1 jet in the leading color approximation to start with. And then, well, different questions arise at this point. So we, of course, want to complete all set of non-planar integrals. We want to unravel the function space. And, well, these integrals are already used for the calculation of Higgs and vector boson plus jet production. We want to compute the full expressions. And then, okay, so we found this sort of counterexample for the adjacency condition, but as I said before, it depends really on the scattering amplitude. It's not really at the level of Feynman integrals where things happen. All right, so with this, I thank you.
Okay. Thank you very much. Very interesting work. I want to ask, so you found these new letters, and then you claim that infrared factorization tells you that they should not appear. Can you explain why?
Yeah, because if you try to predict the poles, like from the Catani-Seymour approach, so you have to deal with the contribution at two loop and then the contribution at one loop, but at most you will have 1 over epsilon to power 2.
I mean, so the letters can appear in the hard function,
Exactly.
even if they do not appear in the infrared singular bit. So,
but that would be already at weight 5. Weight
so
5 and 6.
So your problem is that they appear already at lower
Exactly.
weight that multiplies
Exactly.
singular terms in epsilon.
Exactly.
Okay. Okay. That.
This is recorded, so do you want to first answer?
Why do you say they can appear at weight 5? They cannot appear at weight 5 either, right? Only weight 6, only the finite remainder, but at the level of the amplitude, I would say, because it could still be that for the individual integrals, they appear and then they cancel in the amplitude. But of course, one then could claim you take a linear combination, new integrals, where one of them has these letters only at weight 6, you know, and so there should be possible somehow to rearrange the integrals such that they don't never appear at weight 5 in principle, but I don't know.
I mean, there should be a cancellation somehow. I expect that.
Is this a follow-up?
On page 13, you were mentioning the numerical comparisons. You were also mentioning this fine job thing, but I don't see any numbers there. Do you have any experience on the precision that you reach with that tool?
I do, and I can tell you. Yes. So
Okay,
basically,
question answered.
yeah. So it's like it depends. So first of all, you need to look for integrals that are already finite. Otherwise, it doesn't work. With UV or infrared poles, it's not possible. Then you can to find a finite integral, you can go to 6 dimension. Otherwise, you look in your list of expressions, and there are a few candidates that already are finite. And you just need like an order of 1,000 samples to get a number, something like with the precision of 1 digit. Then if you want more precision, you need more samples, right? For this process, I would say it was pretty well. Yeah, I don't have any problem. And the nice thing is that it's in the physical region. So it's not only the real part, also the imaginary part can be computed in there.
You okay? You want to comment? No. You're...
Okay. Sorry, I'm a bit confused. In the beginning, you show some families, and you have, I mean, all these are known now, okay?
Yes.
A, B1, B2, E1, E2.
Yes.
Just to make sure to understand each other. These are known in closed form in Gonzalez polylogs?
Yes.
There is no integral over something involved.
No.
Okay. Now, what else it remains is this job? It was a bit confusing, your other transparency at the end. So there are many families that are still to be computed?
Yeah, these are the families that we need to compute. So these green ones are the ones that we have already expressed of Gonzalez polylogs up to transcendental weight 6.
Sorry, up to what?
Transcendental weight 6.
Okay. You mean what you say, complete the expansion there? Yes.
Exactly.
Yes.
Then for these guys in here, the dark green, we have the canonical differential equations. And these ones, we have almost nothing.
Sure.
But we have a few candidates of integral, but we don't have the full differential equation.
You don't have, but you say canonical differential equation is there or is missing?
Yeah, for this guy, for
this
the
guy.
dark green.
Okay, and last question, let's go back. 22 families, as far as I know. they have been calculated using the differential equation approach.
Yes.
Now, just a question. I mean, in all cases, you can bring this simplified differential equation approach. So you, at the end, you have to integrate over one variable only. So why you insist, you and your collaborators, to work with two variables? Maybe Lorenzo also can.
Well, everyone does whatever they want.
I mean,
But,
that's what it means. Integrate over one variable is not simpler than integrate over one variable. Maybe I can say something simple.
So I don't know why Johannes insists. I can tell also the other approach, namely that you have like a better picture of the full analytic structure in all variables, and you see the symmetries, and you have like also a final result which is written in terms of polylogs which are linearly independent from each other. So in general, I think what I like of your approach is that you can integrate in this variable x, for example, from 0 to 1 or whatever, and then depending on which value you want, and then you can see in the case of square roots that sometimes the square roots go directly in the letters, right? And you can still have an expression in terms of Gonchar polylogs with the square root in the letters, which in the standard approach is very difficult. If you have square roots, you don't know how to do that. You have to have integrals and so on. But the problem with that is that sometimes when you have these polylogs which are evaluated, say, at 1, because you need them, say, for x = 1 or something, then they're not linearly independent from each other. So when you put them in the amplitude, ours, they are linearly independent. Ours, they're always linearly independent. Yeah. No, ours, they are linearly independent because do it that if an expression is 0, if you take a linear combination of polylogs, it cannot be that this combination is 0. If it's 0, you see it analytically because each polylog is independent from the others. There are no hidden relations among the functions. This is the only difference. I think it's one of the main differences if you want to do the calculation analytically, but it's not tell you what. Not if you have square roots. If you have square roots, you cannot, right? And then it becomes. Yeah. I mean, I don't know. It's just. Yeah. Right.
So I say again, why
Costas, you're just, in my opinion, you're doing is the same, because when you have your expression and then you want to do the vibration basis, you have to do something on top of that. While if you do it in that way, you have already the result in the fibrated version, and you can do the vibrations afterwards. With the square root is difficult now, so we don't. It's not clear. Right. Yeah, maybe we should continue later.
Yeah. Any other questions? Yeah, there's plenty of time to discuss offline. So I think we can finish here and thank William again. Thank you.